I'm Jacob. I work for AIS, and we'll talk about some of my research at HARES, the Hardened Anti-Reverse Engineering System. So in a nutshell, it's about hairs, puffs, and fuzz, or fuzzing, I guess. So it's going to be a pretty cute talk. This is technically an Angora rabbit, not a hare, but a poetic license, I guess. So I work for AIS, the words are my home, out in Denver. We do InfoSec strategy consulting and other research type things. I lead the low-level research team, so we play mostly in Intel rings less than 0. So BIOS, hypervisor, SMM, all that kind of stuff. So in a nutshell, basically HARES allows you to take a binary that you don't have the source code for, and without making any modifications to it or recompiling it, encrypt it, and run it, basically transparently to the end user. We're seeing about a performance impact of about 2% on unmodified processors. There's been some work in the academic sense about modifying kind of a CPU or using an FPGA to do some encrypted instruction sets. This is standard Intel, desktop PC or laptop. It prevents the key leakage or instruction leakage, even to a compromised OS kernel. So if you have a, let's say malicious kernel rootkit, it won't be able to recover the key material nor the decrypted instructions, and the key is actually protected against physical attacks as well. So that's kind of the technical side. What does that mean? That provides a secure execution capability for running sensitive applications, be that you're a vendor that puts out a third-party agent on someone's system and you want to protect that, or you're putting say, an implant on a system that you don't want to necessarily share with the world, and you can run that in a contested environment with a reasonable assurance that it won't be able to be reverse engineered. You can integrate this in the cloud if you want to push something out to outsource your execution without putting too much trust in the cloud provider. This is dependent on encryption, not security for obscurity or kind of obfuscation of hacking. So as long as you trust NIST and the NSA with your AES, which some of us do, you should be pretty good on that side. So the problem statement we were looking into with this research program is algorithms are running on a system you don't have trust as soon as that application or the implant is run on a foreign system. And so it's exposed to copying or theft, reverse engineering. Then you can use that code to develop attacks against it. So you could fuzz an application, find a crash case, and then work through with the debugger to be able to turn that into a remote code exploit. And then also the code can be reused for unintended purposes. So return-oriented programming is a great example of this, of using the existing body of code and then just rerouting computation and execution flow through that existing binary in a different way to get this unintended computation, which is the weird machine from the Langsat perspective. So the current state of the art that we found was obfuscation of hackers. So if you take a program and you scramble it up and you make it very frustrating to compromise. Though there are some automated analysis tools and also live debugging, you can recover these instructions. Kind of the next generation of that is VM-based obfuscation. So VM in terms of a JVM rather than a VMware VM, where basically you create a custom instruction set for your application at compile time, and then it kind of basically runs in this interpreted or just-in-time compiled environment. That requires a source code, and still at the same time it has to be mapped to x86 to actually run on that platform, and so that's also going to impact some performance. The more enterprising solution is just encrypt the entire OS with full disk encryption, add in some trusted boot, and then that way if someone steals your computer off the back of a truck, they won't be able to get your sensitive data. But if someone breaks in, either by stealing a password, passwordlist.xl in the Sony list, in the Sony breach, once you're in, while the system is booted, it's already kind of authenticating. You can access all that data and all that software running. So a little bit of background here. I'm going to mention von Neumann and Harvard architectures pretty frequently. So von Neumann systems have a unified memory and access bus for data instructions. So you'll see here the CPU and the memory, they just talk, and there's kind of no really distinction between how that memory is being used by the CPU. Harvard architectures on the other side, they have separate memories for data and instructions. So if you have a single pointer, if you're using that as an instruction fetch, say you're jumping to that pointer, it's going to go to one region of memory, and if you move data from that or you read whatever is there, you're going to have a separate view of memory. And so in this case, the CPU has separate buses for data and instruction. AES&I is an instruction set augmentation provided by Intel in response to the software caching attacks from MIT, showing that pretty much all AES implementations in software are vulnerable to side channels. And so Intel released a new instruction set, which is put out in, I think, the Core I series 4000 and newer, that basically adds hardware logic and a couple extra instructions to do AES on the CPU in hardware. So it's faster, more protected, supports 128 and 256-bit encryption. It just provides the primitives. You still need to put engineering on top of it. So it's kind of like a nice foundation, but you can still do really terrible things like use ECB or not generate secure keys. But it's a pretty powerful platform. And then some folks at TU Munich built on top of that in Trezor, which is ironically, coincidentally, the name of the hotel tower I'm in. It uses AES&I and the CPU debug registers to provide accelerated and cold RAM resistant attacks for AES. So basically a cold RAM attack, if you're not familiar, memory chips are kind of assumed to be volatile, so you plug them out, you turn your computer off, and they disappear. If you were to freeze those chips by using like canned air, they'll actually persist that memory for a little bit of time. And so you could walk up to someone's laptop or a computer that's locked, but the key has to be in memory, so they can maybe make that be able to check the password you're typing in, and you could actually freeze the chips, pull them out, stick them in another computer, and steal all that stuff that's in memory. So by storing the key in CPU debug registers, that cold RAM attack is not feasible. The key in Trezor, they load at early boot time, so kind of in single user mode before there's lots of other applications and maybe before the networks come up. So you actually have to fat finger it in. It's kind of a good model in terms of reducing risk, but I'll get to later about key management and how that's not necessarily the best option. And then they obviously added a kernel patch to prevent any applications from reading debug registers. So if you open up GDB, the kernel will say, sorry, there's no debug registers available, and it will resort to software breakpointing. So TLB split. This was some work that originally came out for the PAX GR security folks and then built upon by a few others, including ShadowWalker. So the TLB is a cache for virtual to physical translations. So the x86 architecture provides paging and virtual memory, and that allows you to basically create a consistent view of memory independent for each application. So every application thinks it's in a, say, 4 gigabyte flat address space, and there's no other applications running. Before paging came out, every application could have access to the kernel memory or anything, so there's really no protection. So this is managed through page tables that are kind of operated through software and then run and kind of viewed by hardware. It's very slow in the sense that you actually have to hit up to, I think, 7 or 8 times. You have to read different pieces of non-cache memory in the page tables just to access a single byte. So it's pretty slow when you know that cache is considerably faster than memory lookups. And so the TLB basically tries to alleviate that performance hit. Physically, so I guess logically, it's a single entity. It just caches virtual to physical address translations. But it's physically multiple components. So when Intel lays out their CPU on the, into the chip, they'll put one part closer to the data fetch, and then they'll put an instruction part closer to the instruction fetch logic. So they're getting some minute power and performance benefits, but over the life cycle of the CPU, that actually adds up. So what TLB splitting does is it switches x86 from apparently a von Neumann system to a Harvard architecture. So PAX used this to emulate the no execute bit before. So basically, you could say this piece of code can only be accessed as data, and if you ever try to jump to it, it'll fail. ShadowWalker used it for memory hiding. So here's a diagram. During normal operation of your systems, this is basically 100% of the time. Your data TLBs and your instruction TLBs are completely synchronized and they point to the same. So if you are antivirus and you go and read a page of memory and say, that looks safe, let's run it, and then you jump to it, you're going to run what you just read. With the TLB split, they're actually desynchronized, and so that assumption kind of falls apart. And so basically what ShadowWalker would do is it would point the data TLB at your benign existing kernel, and then your antivirus would be, oh, everything's kosher. But then when you actually would be scheduling that kernel module, it would jump to the malicious rootkit. So what is the impact of this? So TLB splitting through software allows you to basically affect an apparent hardware change. The architecture goes from von Neumann to Harvard, and this can be done on a per process basis. So you can give each application a different view of memory. So this is kind of showing off the complexity of the x86 architecture. There was some work by Sergey and one of his students showing that the Intel memory management unit itself was Turing complete without ever actually running an instruction on the CPU. You could simulate any Turing machine. And most endpoint protection capabilities, so PatchGuard, AAV, anti-rootkit, assume this von Neumann. So, they might be looking for time of check, time of use attacks, but they're assuming that if they look at something and then immediately execute it, what they just saw is going to work. And so this basically breaks that assumption and can bypass all of that. And so AV vendors generally leave that off their promotional material. And then the STLB came out. So the STLB is essentially an L2 cache for the Nehalem and newer microarchitectures. So this is the original Core I-series came out, and you'll see in red there's a STLB there, which has bidirectional information flow between the data TLB and the instruction TLB. So this is basically just a larger cache that, maybe if something gets evicted from the instruction TLB, it will still be in the STLB, so you don't have to rewalk the entire page structures. Unfortunately, this breaks that split TLB assumption in the sense that, if something gets evicted from the ITLB, but it's in the data TLB, it can actually kind of flow through that STLB into the instruction TLB. And that kind of breaks shadow walker and it breaks the package share security stuff because you no longer have that kind of Harvard architecture available. So I worked on this program under Mudge, a cyber fast track, that I was looking at doing TLB splitting for integrity verification of applications that interleave code and data on the same page. That we didn't have access to, so it would basically split into an immutable code page and an immutable data page. And that way you can measure this application in real time, and variables and any data writes would go kind of transparently redirected elsewhere. When we started that, we didn't actually know about the STLB, which made it very hectic when it didn't work on any new systems. So we had a couple of months and we realized the only way that we could think of was to use extended page tables to simulate the split TLB on newer CPUs. So EPT, or extended page tables, is part of the virtualization suite of technologies, VTX, VMX, that is basically page tables for a hypervisor to manage multiple operating systems, VMs, as if they were applications. So you can do the same thing. It basically maps what the guest sees as a physical address to what the machine sees as a physical address. EPT has more granular permissions, so you can actually have execute-only memory, read-only memory, write-only memory, or any combination thereof. And so we wrote a thin VMM to simulate this Harvard architecture on a per-process basis. And basically, we would say, all right, if this should be going to the instruction TLB, we'll mark it as execute-only. And then that way, it would never flow through the TLB, or the STLB to the data, because it would basically invalidate that permission. So HARES, what do? You start off with a PE file. So this is kind of the, if you're going to use it in your workflow. So note it's a PE file, so you can give it a .sys file or kernel driver if you wanted to protect something in kernel space, or a .exe for user-land application. It parses out any of the structures and non-executable sections. I'll talk a little bit later about how that's actually probably one of the most challenging aspects of this entire project. Uses whatever AES key you have, and then it outputs the encrypted PE. So all the sections that are marked as executable get encrypted, but the PE headers are still valid. So Windows doesn't it doesn't get angry, and so basically it loads the whole thing into memory and starts setting all the memory up for this application, and then only when the first instruction would be run, if it wasn't being decrypted, would the application crash. So that we can use a lot of the Windows loader to help us. And then we wrote a VMX thin hypervisor. So it's actually based on a VM CPU rootkit. It's a Windows 7 kernel driver. It's a thin hypervisor, so it doesn't do any emulation of devices, and the operating system retains direct access to hardware. So this is not like a Zen where you're going to be running multiple virtual machines. This is no performance hit or very minimal performance hit, and the operating system still has direct control. It doesn't even realize it's being virtualized. And why we want to do that is we want to be able to use certain architectural events and be able to trap on those. So the VMCS, the virtual machine control structure, allows you to set a bitmap of exit conditions. So I want to trap on this or that, and then it will go to the hypervisor before the operating system. In this thin VMM, we then hoisted that Trezor AES code. The It does the key stored in the CPU debug register to prevent against that cold RAM attack I talked about earlier, up into the VMM. And then it adds exit conditions for debug register accesses to either return null or not available, or just silently discard the write. And what's interesting about this is since it's done at the hypervisor level, even an operating system kernel will not be able to access those registers. And then it decrypts the executable sections of the PE into execute-only memory. So this is hardware-enforced execute-only memory. We have some process creation, which basically tells Windows, hey, tell us when you're starting a new program, and we'll check if it's encrypted. If it is, then we'll actually parse out that PE and find the executable regions and set up basically a data structure that we tell the hypervisor, hey, decrypt these into execute-only memory and set up the split between this. And then during termination, we do the same thing. We'll scrub out the program and tell it to stop doing the TLB split. So this is kind of the root of HARES, is this TLB splitting. So all the data fetch requests, even from the application itself, are directed through EPT and the hardware-enforced TLB split to the encrypted page. So this is important if you have an application with a memory disclosure vulnerability. Even that application itself can't access its own code. So you can't use a vulnerability in the application to be able to kind of reveal those instructions. All the instruction fetches are directed to execute-only decrypted memory. And so that's so the application can run kind of transparently, but only if it's being accessed as data does it get redirected to the encrypted page. We also do some, we're not Windows, we're not Microsoft, we don't have any like special agreements with them, so we had to do kind of a lot of brute forcing to make sure that we would be able to track Windows moving programs around, paging it out to disk, moving it around, doing some relocation. Typically when you run multiple instances of the same program, the core kind of read-only executable pages are just kind of mapped copy and write to all the other instances to save memory. But when we were actually changing this, it would actually move our program around and track it down. So we had to kind of keep EPT in line with the OS structures. So there was a little engineering work there, but we had solved a lot of those problems on more as well. Here's a little flow chart right here. So you have this EPT VM exit. Basically, it detects, is this a data or an execution fault? If it's data, it sets EPT to point to data page and says, all right, read-write permissions. The operating system can then actually restrict that down if it's supposed to be maybe a read-only access. If it's execution, it sets EPT to point to the code page with instruction-only access. It sets the trap flag and VM resumes, and then we actually trap on the guest single step, the guest to set the TLB for that guest. And that's kind of how we set this. This is what happens when there's no entry in the TLB. It creates this EPT fault, which is essentially a page fault. And that's kind of how it flows through. So some test cases real quick. We had a couple of them in a synthetic test case. One was very CPU bound and very map intensive. One talked about, just touched a lot of memory, trying non-consecutive cache lines to see how we impact memory. One called a lot of shared libraries to see could we call shared libraries from an encrypted program, and shared libraries might not be encrypted. And then we also did some other performance ones. So the results on average were about 2%. You'll notice one of them like almost doubles, but it's because the execution time is so low. We actually turned off TLB splitting and we disabled the hypervisor and we ran the program unencrypted, but was just basically a no-op process creation monitor, and it also doubled the execution time. So the Windows kernel callback for that essentially doubles or adds a constant 0.015 seconds for each test case. And so since that randomized sort ran for such a short period of time, the performance impact was relatively huge. We also wanted to make sure that we could encrypt programs that we don't have access to. So Notepad, Paint, and Calculator, we don't have the source for. And then also that there was no end user impact. So we encrypted Notepad, Paint, and Calculator and just tested them as if we were doing our taxes or something like that and writing a batch script. And there was no noticeable impact. The performance was very minimal to the point where we had no idea. Notepad and Paint and Calculator are interesting applications as well because they're pretty old. I think Notepad was last compiled in like 2006. It was on Windows 7. And so it has some very interesting features that I'll talk about in a little bit. So our demonstration system, so I'll show you a video because this Mac doesn't actually have the Core i-Series processor in it. And we kind of made some assumptions right here for the prototype system where we can just turn some stuff off, though it's mostly just an engineering work to remove these restrictions. So that said, let's see how terrible the resolution is going up here. So you're going to see on the right, our command line test suite is going to be calculating pi in a very inefficient way. So there it is, getting closer and closer. We attach the program with IDA. It's very refreshing. I don't need to tell people what IDA is compared to a lot of the places I talk. We find the text section in the entry point of the program in IDA, so we're basically going through, and then we tell, all right, start, decrypting it or disassembling here. And you'll notice when you actually run it, that this code is actually valid. So this is, kind of setting up the stack, making some jumps and calling some kernel function. So now HARES, we're going to run that PE mod encryption program on the right. So you'll see here we're basically running that same program, and now we're running it again. It's doing the same process of calculating pi, same process here. I have a longer video that I can show another time, like over a drink or something like that, that I don't have time for right now, that shows us single stepping through the program and either freaking out that we're jumping partway through an instruction, or we just executed something in what it thought was data, or invalid instructions, and the program is still happily churning along. So if you look at this, basically the program, it's completely junk. We just returned from a function to NCDLL and we stepped out, and the call to that DLL was like an AAM, which is some like crazy extension instruction. So it's not, this is just IDA trying to guess what that is based on random data. So that's just a quick little view right there. So engineering challenges, the biggest one is the code and data mix in the same PE section. Window that I talked about are relocating and paging out the application memory. So mixed code and data. So Notepad, since it was compiled so long ago and everything was at a premium in terms of space, they actually just compressed all the sections. So there's really a lot of these strings and stuff like that. Like this is the statistics button that gets labeled, the GUI label. You see that it's right there on the bottom in the same section right below a function. And so when we were encrypting that, we were taking that string and encrypting that as well. And then since we wanted to protect against those memory vulnerability disclosures, we would not let even the program itself read those strings. And so what would happen is it would read an encrypted string. In some cases it would just show up as garbage, but a lot of times the null terminator gets encrypted and then lost. And so it would actually like buffer overflow itself as it tried to draw the GUI label. So that was the most frustrating challenge, and it's a very difficult challenge. So some of them are really easily identifiable. So import tables, debug tables, they're all parsed and you can just exclude them from execution. Those strings, like I just talked about, statistics, they're sometimes stored. So if we have the source or we're writing our own software we want to protect, we just set the compiler option and say, don't do this. Put all the data somewhere and then mark it as non-executable, and then we're all set. If we only have the binary, there's kind of three solutions. If we have debug symbols, that's fantastic. We can just say, all right, it's a data debug symbol, just don't encrypt it. The worst case is reverse engineering the entire binary, which is basically a non-starter for any program, much larger than basic one. And then we built basically provisioning or learning mode. So this is kind of like app armor when you put it in learning mode, where it will log all the infractions and then you kind of go through. So basically, we'll run the program with the split TLB when it's unencrypted and just track where all of those kind of self-referential data instructions or accesses are on, say, a trusted system before we're going to deploy this application. And it will learn where all those are, and then it will create basically a mask of regions to not encrypt. And that's a way that we can basically keep those statistic strings unencrypted and the program's still working. So this kind of assumes you can provision it on a safe system. So security benefits, protects against reverse engineering and theft of your algorithms. Going and weaponizing a crash case to remote code exploit is much more difficult. Mining that application source for ROP gadgets, also much more difficult. And then the Harvard architecture by itself is resistant to code injection attacks. So sometimes you'll attack one program and then you'll use some kernel functions to basically open another process's memory and put your payload in there so that, if someone goes back and is doing some instant response, they say, oh, this program right here is one that was compromised. Let's not focus on patching Apache. Let's look at Word. And so in this case, even the operating system can't overwrite the code that's going to be executed. It would overwrite the encrypted data, but that program would actually never get run. So the hardware architecture has some security benefits as well. And so if you're using this on a security sensitive application, you can kind of draw those benefits. So this was written up in Wired, and it sounded like hackers were pretty much done, and they're all going to become cooks and truck drivers. That's not necessarily the case. There are plenty of weaknesses. So the first one, JTAG, ICE, and XDM. So this is basically a hardware debugger. So I have one at my office that sits between the CPU and the motherboard, and I can basically start single-stepping through BIOS. I can trap on system management mode interrupts, trap on hypervisor, and I can see everything. And with that, I'd be able just to boot the system up and pull the key out of memory, no problem. Memory dumping, the cold RAM attack, will not be able to recover the key, but it will be able to recover the decrypted instructions. DMA was shown in Trezor Hunt, which was a kind of an attack paper against Trezor. That if you had a compromised device, or you could kind of pivot through a device, the protection schemes that say this is not readable or this is execute only, don't work. They're not enforced against a device. And so if you have a device with direct memory access, you get around that. System management mode, or AMT, basically more privileged modes of the CPU, or AMT is a separate processor that runs, that still has full access even when your computer's off, but is kind of a side channel basically, in the sense that it's a separate processor running a separate operating system. Those are there, certainly would be able to recover decrypted instructions or just the key in general. I'm sure there'll be side channels. I'd be very interested in people who like to play in that space. I just out of curiosity, but I don't know what they are. The most, I would say, most likely one would be if you could coerce HARES to run in a nested hypervisor or in an emulated environment. If so, you could pretty much render its debug register protections null and void and just steal the key and then decrypt whatever you want. Another one, which is another interesting kind of semi-side channel, is looking at syscall and then kind of inferring, or system state changes and inferring what the program is doing. Kind of not necessarily seeing exactly what instruction, but you might be able to kind of look at the system as a whole and see how it's changing, see what system calls it's calling, and be able to kind of infer what it's doing to be able to at least get a little bit better of an idea. And so that one, again, is just a weakness in the sense that if you can watch anything and then you have to do some black box reverse engineering. So we have a couple ways to get around that. So VTD is basically a set of page tables or an IO MMU for the devices on a PCI bus or a PCI Express bus, and that would prevent against DMA. So you could actually say devices can't talk to this region of memory, and they won't be able to recover that decrypted application. The Core BIOS project has a cache as RAM capability, so they can actually run and load stuff right to the cache without actually touching memory. And so in this case, CPU caches are in the maybe tens of megabytes these days, so you'd be able to run at least the sensitive part of your application in the CPU and never actually flushing it back out to memory. And so in that case, a cache as RAM attack or a cold RAM attack would not be able to recover the decrypted application. To prevent against VMM, we have basically a trusted launch. So that could be Intel's trusted execution technologies or AMD's secure virtual machine or some software-based equivalents. And that basically can ensure that you're not running in a virtualized environment before you load that key. And that key can be stored in the TPM or some other place I'll talk about in a minute. Some interesting future work, I think, would be there's some academic work on unique compilation, where every time you compile the same program, it'll compile it differently in such that there's certain invariants. So maybe this program that was compiled today is vulnerable to this class of attack, but if I compile it again, it will be vulnerable to maybe a different class of attack. And so you'd be able to combine this and then create each output binary as completely opaque. And so that way, if you're trying to attack, say, Apache, you need to have the one that's running on their system, which means you already need to get onto their system, because if you just get the binary, it's going to be opaque, you're not going to have the key, you're not going to reverse engineering it. And with this, you you can't basically attack all of Apache, but only the specific one that was compiled. So that's another interesting kind of future use case and kind of de-incentivizing 0 days by making them very, very specific. Some of you guys might know this guy. There is some other use cases, right? And so I presented some of this stuff at Syscam, and some of my malware analysis friends were very upset that their job is going to get much more difficult. So offensive key management, though, I think is kind of where we need to look, because on the defensive side, it's very easy to deploy this. You can have everyone's agreement, you can use existing PKI and signatures and TPM, and so kind of doing this when everyone's on board is not too bad in the key kind of deployment. But when not all parties are in agreement, it's actually much more challenging. How do you get the key on there without it being covered, or how do you kind of make sure you're on the system you think you're on and you're not being running this VMM? So offensive key management. So this is some stuff that I'm trying to work on now, kind of moving forwards. So a boot kit for key loading, so you can kind of persist through a reboot and that's what you want to do. So this is a paper called Conqueror, which is basically a software root of trust measurement program. And it allows you over a network or to another trusted device, basically it's a timing attestation protocol, and it allows you to detect, is there an emulator running, is someone debugging me, is there a hypervisor that's even trying to hide, because there are certain CPU instructions that will actually trigger a VM exit, and you can basically do some timing analysis to determine. So that would be how you could put stage 1 of your your drop program on there, figure out and map out maybe this target right here is too well protected, or it would not be safe to drop the actual payload, and then you could find another target. Or you can say, oh, there's no VMM running, I can kind of map out the space, and then you could come back. So puffs, physically unclonable functions, are a way to expose manufacturing variants in a way that you can get machine unique and, it's in the term, unclonable functions. Technically, you can clone them if you have a fib, but that's kind of outside the scope of this. But you could actually create a TPM in software that has a device-specific key, and with HARES, you can then get a protected execution environment. So you could basically create, trusted computing for offensive capabilities. And so this would allow you to basically make sure that the software you're running is only running on the systems you want it to, because this puff is basically machine unique, and that the keys are all protected. So this is actually a pretty interesting path forward as we're looking at. And then also, what lessons can we learn? We're constantly kind of making fun of and lampooning all of the enterprise PKI management and all that software. But there's some challenges there that they've had to overcome, and they have some ways of doing that. What can we draw on that now that we want to create basically an offensive PKI to be able to have basically trusted exploits and trusted implants? So we looked also at AV heuristics. My malware analysis friend that was almost in tears said, well, it doesn't even matter because your payload is going to just flag instantly as malicious, because the entropy of those instructions is all off because you basically just ran the data. So I took notepad.exe, I encrypted it with, I think, the key like 123 or whatever, uploaded to VirusTotal, and sure enough, actually 4 out of 57 AVs flagged it as malicious, which is not that much. And if you notice, I don't know if you can see, it's super blurry, but the results is all heuristic based or packed or basically entropy based. And I sent the sample to AVG, which is the top one, and I had their analysts look at it, and they said it's just because of the entropy. If you sign that binary, so this is again something a challenge for the offense, is if you were to sign that binary, all the heuristic ones would just kind of bow out, and so you actually get complete protection. So to get some ground truth, though, I took notepad.exe and uploaded it to VirusTotal to make sure that no AVs flagged Notepad. And sure enough, no AVs flagged Notepad, which is good. They had a little thing that popped up today. Yeah, this is actually published, and this SHA-1 hash or SHA-256 hash matches that, and it's published by Microsoft, so of course it's not a virus. So I was just curious, I opened up in a hex editor and I found like some compiler version string, and I changed it by 1 bit. And then I took that same unencrypted Microsoft deployed Notepad, uploaded to VirusTotal, and then 4 out of 57 AVs also triggered it. A different set, which was very interesting. So I guess the end of the day is your odds are pretty good on the offensive side, because AVs have no idea what they're doing in most cases. So it's pretty good. So There is some related work, so Truly Protect, it's basically running a AES-based VM obfuscation virtual machine in terms of the JVM running in cache. And so that decryption is all happening in the cache. Private Core, which got bought by Facebook, is a Linux kernel running in the cache that has a key loaded in that CPU cache. A very, very small Linux kernel, obviously, and you can run programs that are encrypted outside the cache, and as soon as they kind of move in, they get decrypted and run, and then back out. Intel SGX, their secure guard extensions, is basically you can support a HARES-like capability of having enclaves that are protected against maybe a malicious kernel, but it's using hardware. So this still is kind of an evolving, soon-to-be-released holy grail of security, working towards that kind of Palladium trusted and opaque execution environment. So the TPM was just one stage. That was more for data and device attestation, but now you want to be able to do execution attestation. And so SGX is kind of the next stage. They've done a good job of not bringing up the P word, which most people would freak out about. So in conclusion, I think I'm a little fast, but so we were able to demonstrate the viability of, on unmodified hardware, encrypted execution. And then now we're having to ask the question, okay, we found that, now what? So offensive key management and offensive kind of trusted computing becomes a very interesting new field. It, as it stands, significantly increased the reverse engineering difficulty with very minimal performance impact. The CPU performance is almost negligible. It does increase the amount of memory you're using. And it provides these legacy systems some breathing room. So if you know that your program is probably vulnerable because it was written a long, long time ago, but you have to run it for business continuity sake until you can replace it with a newer version, you could encrypt it to at least make it a little bit more difficult and get some breathing room. And I'm really excited to see what happens with SGX, because I've heard from a lot of Intel folks that this is really the platform where they learned all these lessons from TXT and all the stuff from the Invisible Labs folks, and really kind of came together with a really solid hardware extension. So I want to thank my coworker, Mudge, and then a couple other folks for their input from a reverse engineering perspective. A lot of references, which I have a white paper for. Thank you. And so if you go to my Twitter account, the pinned tweet has a link to a 12-page white paper, which has all the references and all the figures and a whole bunch of background that I wasn't able to go over. So I think I have a little bit of time. I could actually show the slightly longer video unless there's a lot of questions.
Oh, we do have questions, so
okay.
Let us hear the amazingness of questions.
Hey, it's kind of a sort of a basic fundamental question that I didn't understand. How does your VMM determine whether a particular fetch is an instruction or data fetch? Is it possible for a compromised operating system to trick it or to directly modify those EBTs?
The EBT is only controllable by the hypervisor, and the VMM itself actually doesn't really detect whether there's an instruction or a data fetch. That's done in the CPU, so that's using that TLB splitting, and it's kind of activating different pathways through the CPU. And so as long as you set the EPT partitions for the execute only on the instruction fetch, all instruction fetches will go through that instruction TLB. And then all data fetches will go through the other one, the data fetch TLB. And that will then protect the encrypted or decrypted instructions from ever being read as data. And so that's kind of below the VMM. And this is kind of, the TLB is basically a performance enhancement. You could single step in a hypervisor and then determine if it was an instruction or a data fetch and then switch. But the TLB and the split TLB makes it, basically usable from a performance standpoint.
When you discovered the STLB existed and used the EBT, didn't you essentially have to abandon TLB splitting and rely on the EBT, kind of read, execute, write bits?
Yeah, so we're simulating the split TLB in the sense that the behavior is the same to all the software running of having a split TLB. And there's actually some open discussion with some folks of trying to figure out the exact logic of how that kind of flow through happens, of whether or not it will just never put out to the instruction TLB of EPT that doesn't have the permissions, or if it will, and then just kind of once that actually gets read, it will then fault. And so this is simulating a split TLB in the sense that the hardware no longer has a split TLB, it's one shared entity, but we're able to kind of, from the all intents and purposes, split that TLB in the sense that all software is running as if it had a split TLB. So the performance is the same as if it was running in a pre-Nehalem system, but yeah, technically at the hardware level, there is no more split TLB, and it's kind of moving back and forth like that.
I guess I'm just curious as to, why are you using the terminology of the TLB with your new EPT technique?
So the EPT technique is just the performance enhancement from having those TLBs and being able to kind of isolate them is where we're getting it from. So the package GR security, they were using, basically page table isolation and the user supervisor bit that they were overloading for this. And they were just using the TLB splitting for the performance benefits. And so it's kind of the same nomenclature that I've been using in the sense that the TLB is a great performance improvement, but technically all the stuff is being done in page tables and using permissions and modeling. So great question.
And sorry, one more. Could you just tell us the story of how you discovered the STLB existed? Because I think that would be funny.
Okay, so as you folks who know, Cyber Fast Track was very short projects. I think it was like 3 or 4 months was this one. And it was just when the program was starting up, so we had really no basis. And we started working and we built our first prototype, and it had monthly drops. So you could drop it off and run it on their systems, and then they would verify, and then they would pay you if it worked. We actually were running on an older Core 2 Duo system, and everything was working great. We sent it the thing and said, here's how you run it. It didn't work. And going back and forth, and then we realized when one of my coworkers got a new computer that it was not working in his system either. And so then we started looking through the software developer manuals, and I had an old version that I had downloaded or got the print copy from the Core 2 Duo errors in it, so it didn't even have that STLB picture in it. And then looking at the most recent ones, I was like, oh crap. So yeah, it was very hectic there for a little while trying to get paid, but it ended up working out all right.
I think you have a question, right? And I hope it's about offensive implant protection.
Unfortunately not. No, I was just wondering if we were going to see implementations like this from your team on OS X or Linux anytime soon.
So at the architectural level, there's really no reason not, but we haven't. It's just an engineering point. I'm trying to push to have all the stuff open source once we get a little bit more stable. And at that point, it would just be kind of a pretty simple porting job. I mean, the VMM itself is just using architectural features. So pretty much you'd be able to hoist that and drop it on another environment. And then just kind of that process creation monitoring and the hypercall and that kind of stuff would be something. And then obviously, ELF files versus PE files. But I mean, there's no, reason why it couldn't be. It's just, this was what we were basing on.
So the using the split TLB pre the new architectures was more or less unintentional feature, unintentional architecture design, and then it was obsoleted when they implemented the STLB. And when you're using EPT for it, is that the intended use of the EPT, or is that something that could be obsolete in the future as well?
So yeah, the EPT, it is another unintended thing. So yeah, there could come out a future one which would basically preclude having this type of thing. But for now, I think it's going to be around for a while.
That was a surprisingly good question. Okay, so people, when they ask questions, like to give me the smallest possible indicator for some reason. I don't know why that is, because I guess we're all really shy. So if anyone wants to wink slightly or nod, or that.
So for key management, you mentioned memory dumping. You can potentially, I guess, recover the key and decrypt the binary. How does that play out with hibernation files? Does execution persist hibernation, or does it in a VM snapshotting?
Sure. So the key is actually not in memory. It's on those CPU debug registers. And depending on what sleep state it goes into, those actually might get lost and have to be reloaded.
Okay.
And a VM snapshot if you're running in a VM environment, and at that point, the VMM can just pull the keys out. If it supports nested virtualization, and so there's really no reason to leave a snapshot. So that's what we're trying to defend against. So either, running it as part of and a kind of implicit. So Microsoft 8 basically rolled out hypervisor for every install, and I think 10 is making it basically mandatory. So if this was integrated with that, you'd be able to basically have kind of that that environment, in a defensive situation. But if you're just trying to attack it, if you can get the system to run in a nested virtualization environment, then going through the whole snapshotting process is really too much effort.
What about running more complex programs or even JIT code?
Either what?
Even just-in-time compiled code?
So that was something that was future work in the sense that it's being basically, you're converting data into execution and code, and that's something that is basically the same as self-modifying code, which, basically your JIT code, as soon as it starts being JITted, will actually get on the encrypted data side, and it will be able to be read, and it will also not execute. So at present, that would be something that you'd have to kind of instrument your just-in-time compiler to say, all right, this is going this way, and you can maybe make something that's write and execute only, so it can't be read in that regard, which is kind of the opposite of most traditional stack buffer overflow defenses.
Who do you think are going to be the first adopters of this? On the defensive side or on the offensive side, from a nation-state perspective or from a primary perspective?
So I think from a defensive side, they just have so many other issues, like at the point where, they can't manage passwords properly. So I don't see them ever wanting to worry about this. Whereas, on the more offensive side, you have people that spend months reverse engineering and figuring out, trying to find tiny little vulnerabilities to be able to break down an obfuscated binary. And so I think this is going to, just because of kind of the environment, offensive capabilities need to be much more stealthy. Whereas on the defensive side, this is like that last 5% of protection. People, if you can get your HR staff to not click on links in emails, I know our HR staff, we had one I saw, they had more screen real estate dedicated on their browser to browser plugins, the Google toolbar, the Yahoo toolbar, the Azure toolbar, and the smiley faces, like multiple versions, they could be really smiley, than actual screen real estate on this 24-inch monitor to browsing the internet. So, at that point, I think they have bigger fish to fry in terms of their return on investment. Whereas on the offensive side, you're protecting a very small amount of code that is going to be very highly scrutinized. So that's what I would say.
And then the nation-state side or the crimeware side?
I think nation-state side first, in the sense that they're undergoing more scrutiny. It seems like you see this crimeware packages get leaked all the time because people can't get their act together. And then also, for a lot of this stuff, like this top-tier crimeware stuff, they don't need to be very malicious or sneaky because people won't patch your system. There's still people running XP. So if that's, your target space, spam still works. I still get, Viagra spam. So if that's going to make someone money, why would you bother, invest time trying to figure out this stuff? It's going to reduce your ROI.
So it sounds like most of the work going forward has to do with program, or at least a substantial amount of it has to do with programs reading their own memory, modifying their own program space. Is it reasonable for the VMM to allow that process alone to read its own memory while excluding all their attempts?
Yes. So that was how we initially set that learning mode. We would permit that application to basically, we would permit it anyone, but we could basically say if the EIP is within that process's own address space, we could allow it to read its own memory. And so we could do that, though there is some significant security drawbacks to that. That might be the easiest way, is basically let everything in that process space kind of act as if it was kind of outside the scope of this. And then everything outside of the process, it would be opaque too.
And then also, what's the implementation right now? Is it available, or?
The implementation for more, which was the TLB splitting for verification, is open source on GitHub, and I'm trying to clean up the HARES stuff and then hopefully release it sometime this year. Also as open source.
I just wanted to make a comment because you asked about using it offensively versus defensively. I think one thing to keep in mind with this is if you're going to use it offensively, at least on Windows, most Windows are 64-bit now, and you need a signed driver to drop something like this. So that alone would require pretty sophisticated exploits to get to that level. So I don't think you would want to use something like this for just your average exploit that you want to get on lots of systems. It would probably be a much more focused.
I guess that implies no kernel level vulnerabilities exist in Windows, which is good news.
Kind of conflicts with the HTTP vulnerability that they just released today or yesterday.
What HTTP vulnerability? All right, so we're gonna pause briefly for a coffee break. And I want to point out that many of the past keynote speakers for Infiltrate are here, and you can actually heckle them for their past keynotes as well, especially Andrew Cushman. Thank you very much. Did we get a chance to clap? I can't even remember.